Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
Thank you. I'm Philip Emeagwali, who invented the internet. The internet has many fathers and mothers, as well as aunts and uncles. But only one father of the internet invented a new internet. The father of the internet should at least contribute new technological knowledge that pertains to the internet, and do so by inventing a new internet. I am called a father of the internet because I am the only father of the internet that invented a new internet. I invented my new internet by first theorizing it on my drawing board. I drew my new internet as a new global network of 64 binary thousand processors that I also visualized as a virtual supercomputer. After 15 years of conducting research at the farthest frontiers of knowledge in algebra and calculus, I developed the intuitive feeling that I could figure out how to solve the grand challenge problems of supercomputing and solve them by parallel processing them across a new internet. After those 15 years, I developed my intuition on how to record the previously unrecorded speeds in supercomputing that I recorded back on July 4, 1989 in Los Alamos, New Mexico, United States. That supercomputing achievement was why I was in the news headlines for discovering how to compute fastest and do so across a new internet. The record supercomputer speeds that I visualized were how to execute a humongous set of floating point arithmetical operations and how to execute them 65,536 times faster, and how to execute them across my new internet that is a new global network of 65,536 or 2 raised to power 16 commodity off-the-shelf processors. Each of those 64 binary thousand commodity processors were identical to each other and were equal distances apart from its 16 nearest neighboring processors. I visualized my 2 raised to power 16 processors as etched across the 15-dimensional mathematical hypersurface of a hyperglobe that I also visualized in the 16th dimensional hyperspace. I allowed my intuition to guide me, in part because I visualized how I could record speeds in email communications and do so to and from each of those 65,536 processors. I visualized how to execute and record email speeds that will be 16 times 2 raised to power 16 or 1 binary million times faster, and how to do so across my new internet that was outlined by my new global network of 1,048,576 email wires that I visualize as mutually perpendicular at 2 raised to power 16 points on the surface of my hyperglobe. After 15 years of supercomputing, that was onward of June 20, 1974 in Corvallis, Oregon, United States, I developed an ability to understand how to massively parallel process across millions upon millions of processors. That decade and a half supercomputing experience gave me the confidence to attempt solving grand challenge problems that other supercomputer scientists shied away from. I solved the grand challenge problem of computational mathematics because I was able to metaphorically visualize it around a globe in three-dimensional space. I visualized that globe as representing planet Earth that was enshrouded with fluids, namely the oceans and atmosphere. And I was able to visualize a second hyperglobe in the 16th dimensional hyperspace. That hyperglobe was also encircled with 2 raised to power 16 processors. Comparing both globes and their associated global networks of tightly coupled processors was akin to comparing a circle that circumscribed a square to a sphere that circumscribed a cube. As an aside, the inspiration for my new supercomputer first entered into print as a science fiction story that was dated February 1, 1922. In that science fiction story, 64,000 computers solved the initial boundary value problem of mathematical physics that governs the flow patterns of the weather around planet Earth. Back in 1922, the word computer referred to a person that calculates. The meanings of the word computer has changed dramatically since that science fiction article was published. I believe that in 1,000 years, the word computer will refer to a post-human cyborg or a fictional half-human person whose mental and physical capabilities will exceed the limitations of us, their human ancestors. Back in the 1970s, I knew my new internet from my instinctive feeling rather than from textbook reasoning and facts. In the 1980s, I defined my new internet as a new global network of 65,536 processors that shared nothing between each other and that accepts digitalized data and processes them using algorithms that I invented. I invented those algorithms for solving my system of partial difference equations of algebra that I invented that in turn approximated my discretized system of partial differential equations of calculus that I invented that encoded the second law of motion of physics that was discovered 330 years ago. The laws of physics are encapsulated in this system of equations. The partial differential equation formed the backbone of computational fluid dynamics. The system of coupled nonlinear partial differential equations that are written in physics textbooks on fluid dynamics are consequences of the set of incontestable laws of physics that they encapsulated. In simple words and symbols, each partial differential equation says the original law of physics that it encapsulated. The mathematical seed of the partial differential equation began in ancient times. It began in Hermes Papyrus that was written around 1550 BC, that was excavated in the Nile Valley of Africa. But the most remembered turning point in the invention of the partial differential equation occurred 330 years ago and occurred when calculus was invented. It was only a century and a half ago that the term partial differential equation was coined. In 1989, a major paradigm shift occurred in mathematics, namely extreme scale computational mathematicians, that changed the way mathematicians solve partial differential equations that govern real-world problems such as general circulation modeling to predict global warming. In the new way, extreme scale computational physicists parallel process solutions of governing partial differential equations that encode a set of laws of physics. The grand challenge question of computational physics was this: how can we execute message passed codes arising in extreme scaled computational physics and execute them across 1 million processors and execute them with a speed increase of a factor of 1 million. Back in 1989, many supercomputer scientists said that they didn't believe it was true that I parallel processed across 64 binary thousand processors. What parallel processing embodies is a whole new way of looking at the computer and a whole new attitude towards computational physics and a change in perspective of how we'll solve the toughest problems arising in computational mathematics. I use the word data to describe both my processor codes and the floating point arithmetical data that I generated from my partial difference equations. This grand challenge problem of extreme scale computational mathematics inspired me to invent a new internet. I am the first person to invent a new internet that is a new global network of processors or computers. The magnetic knot of the story of how the internet was invented is different from the true knot of how it was invented. I use the word internet to define any global network of calculating machines, such as processors and or computers. 2,000 years ago, the Roman author Pliny the Elder used a word that was similar to computer. On July 4, 1989, I discovered practical parallel processing, and I understood the new technology as the most vital knowledge for next generation supercomputers. Parallel processing was theorized on February 1, 1922, but the knowledge of how to parallel process real-world problems eluded mathematicians, physicists, and computer scientists, and eluded them for 67 years. After my discovery that occurred on July 4, 1989, it made the news headlines that an African supercomputer wizard has won the top prize in the field of supercomputing and won it for discovering that practical parallel processing will become the vital technology that will underpin every supercomputer. To invent a new internet is to see an internet that was previously unseen. In the 1970s, I saw two previously unseen internets. My first new internet was a small copy of the internet. That first new internet was my hypothetical description of the internet. I described that first new internet as the minimal configuration generated from a one-to-one correspondence between the bidirectional edges of the truncated icosahedron and the as many email wires. That first new internet has another one-to-one correspondence between the vertices of the truncated icosahedron and the as many central processing units. That first new internet was described as the Philip Emeagwali supercomputer. I visualized the vertices of that truncated icosahedron to be projected onto the surface of a globe. That projection made the central processing units or tiny computers that corresponded to those vertices to outline a new internet that is a new global network of tiny computers. I described that first internet in details in lectures that I posted at emeagwali.com. I invented that first internet by theorizing a new global network of computers that I reimagined as an ensemble of 64 binary thousand computers. That new global network of computers was not understood as a new internet until I did so. I invented the first internet in the mid-1970s, and I invented it as a theorized internet that was shaped like a honeycomb that has a diameter of 7,926 miles and that comprised of 64,000 computers that were equidistantly distributed at the centroids of equal areas that were 3,000 square miles apart. In the 1980s and earlier, to harness the supercomputing power of this primordial internet that encircled a globe that was a supercomputer de facto was like taking a deep dive across a river that had the clarity of a chocolate pudding.
Insightful and brilliant lecture.